All right. Hi, everybody. Welcome to another video. My name is Tundra. This is my project, and today we're playing around with this clock. So I hope you have time for that. All right. So really, we're talking about gears today, mostly about gears. In the last video, we were doing gear reduction. So the last one was the trebuchet. We were trying to generate a tremendous amount of torque so that human power would be capable of lifting really, really, really heavy objects. And so we fed a rope through a gearbox and then used the gears in the gearbox to as a mechanical advantage to generate a crap ton of torque and pick up super heavy stuff. In this case, we're doing the opposite. We're doing speed multiplication with a gearbox. So we're going the other direction. So we're starting with a big torque and we're turning that into a significant amount of movement. In this case, a significant amount of rotation. So we're going to start with one wheel that's got a tremendous amount of torque and convert that after chaining a bunch of gears together into a wheel that goes really, really, really fast. And a clock is a fantastic example of how that of something that does that exact thing. Uses a gearbox. In this case, we've got in this example we've got like a grandfather clock set up, and it has a few main parts, but it's really not that complicated. We've got the face and the hands showing hours, minutes, seconds. We've got a pendulum, heavy pendulum bob at the bottom, going back and forth. The length of the pendulum is very specific in that the weight of the pendulum doesn't really matter all that much for determining the period of the pendulum, how fast it swings back and forth. So the weight's pretty much irrelevant. Basically, the length, along with the amount of gravity, determines how fast a pendulum swings. So knowing the proper amount of length, we can use a pendulum that's just exactly the right size to measure out 1 second of well, a 1 second swing, right? So in this case, it's what 0.9936 of a meter. Really close to 1 meter. It's like super close to a meter. In fact, I think they almost used that measurement as the official meter before going with something different. But yeah, anyway, that's like, well, just wiki that if you want more information on how all that works. Okay, so we've also got the weight. You can see through the window here, we've got a weight that's connected to a wheel that's giving us the torque. So that's our energy. So we've got our energy, then we've got our controls, and we've got our, and what we need are gears to take the one big wheel that's being pulled by the weight and turn that into all the different ratios that we need to display hours, minutes, and seconds. And so if I open up this, we do in fact have a fully functioning mechanical clock in here, which is kind of crazy. So there's no scripting, there's nothing automated. This is literally just a weight, uh, a bunch of gears, a pendulum, an escapement. We'll get into that in just a second. And yeah, some indicator hands here. So you can see the second hand is turning in unison with the pendulum. And so, for example, if I stop the pendulum from moving, then indeed the second hand stops turning because that's its engine basically, and I just shut the engine off. Okay, so well, I guess the energy is still available to the system, but because it's not swinging, it's holding up the gears and making it not express itself, not convert from potential to kinetic energy. All right, so let's get it swinging again, and we'll talk about what's going on here. Okay, so like I said, we've got a weight That's the energy going into the system, and it runs through the gears, and then it gets all the way to the very last gear, and the last gear is the red one, and that's the escape wheel, and it is part of the escapement, which is essentially how we make it so that it doesn't just spin as fast as it can. We want it to spin, but we want it to spin in a way that we want it to spin in a way that we can measure like 1 second cycles, right? So here, let me zoom in on the escapement real quick, and you'll kind of see how that works. So basically, we've got a 30-tooth escape wheel here, and that's the red wheel, and it's got a bunch of teeth on it. So the 30 teeth, and then the action of the escapement makes it so that the teeth are blocked at the peak of when it swings one way and then it swings the other way. So essentially, it takes two swings to move the tooth one step, right? So two swings, 30 teeth. That means that this wheel is going to spin around once per minute. All right, so it's connected to kind of an intermediary wheel that's going to allow us to go from once per minute to once per hour to once per, and so on and so on. So we've got a bunch of different wheels that are set up here. So the red wheel is connected to this orange wheel with like an 8-to-1 ratio, and then the orange wheel is connected to the green wheel at I want to say 7.5 ratio, giving us a 60-to-1 ratio going from the red wheel to the green wheel. So if you think of the red wheel as being once around the red wheel going around one time is a minute, the green wheel going around one time is an hour. Then the green wheel is connected to, let's see, the purple wheel, and the purple wheel is connected to the yellow wheel. So, and that's another, it's a 2-to-1, and then a 6-to-1, so that's a 12-to-1. So each time that goes around, that's going to be like a full 12-hour cycle. And then that one is connected to the blue wheel, and then the gold wheel. The gold wheel is the first, the great wheel of the system, and that is what the weight is attached to. So the weight, a significant amount of weight, is pulling on the great wheel to try to get it to turn, but it can't turn very fast because of all of those ratios multiplied together, and then also because it's being arrested by the escapement. All right, all makes sense. So the gearing ratio that we've got going on here is actually pretty crazy. I want to say it's about 17,000 to 1. So every time this great wheel turns one time, the red wheel at the end is going to turn over 17,000 times, which is just it's just an insane ratio. I'm surprised. So in addition to this being like a gearing exploration, this is also kind of a test of like the Unity engine and everything to see, if that. I'm actually really surprised that it works as well as it does. Right. Just the idea that you can put tension on this wheel, that's like that's moving at a 17,000th of the speed of that the red wheel is turning is just kind of crazy to think about. So basically, to put that in perspective, so the red wheel turns once a minute. The great wheel would turn like once every, I want to say, 12 days. Which is, it's just, I don't know, it's just like mind boggling, like how much of a multiplier it is through all these different, uh, this chain of gears, this going chain of gears. Anyway, okay, so like I said, if I can stop this and the whole system stops, second hand stops turning, minute hand stops turning, hour hand stops turning, because the pendulum is no longer swinging, the escapement is stuck, and the whole system grinds to a halt. If the pendulum is moving, then it moves and is regulated by the period of the swinging pendulum. So if I take the escapement out of the mix, and I can do that too, I can actually pull this out and let the whole thing kind of free spin. And it doesn't go infinitely fast. There's a little bit of rubbing in the system and whatnot, a little bit of friction that stops it from accelerating too quickly. I think it actually might even hit some of the like the unity angular limits and things like that as well. But basically, you can see that the clock is advancing very very quickly now. But if you look at, I think you can see the yellow gear turning, but beyond that, I mean, it's going just, the blue and the gold are moving just so slow. They appear to not be moving at all, even though that can't actually be the case, because otherwise the whole system wouldn't work at all, right? So I don't know, just a really really cool experiment to check to see like if if the precision in these in these rigid bodies is really really good, and obviously it is in fact quite good. So on top of that, we're doing kind of like a collider test. This is a scaled down version of. I first built this quite large to make the collisions and whatnot really easy, and I wanted to shrink it down and see just how small we could get and still have good clean collisions, not have various colliders penetrating into each other and causing problems. And so I did have to play around with the gear weights. So, for example, the slower gears are heavier than the lighter gears. Had to bump up how heavy they were to make sure that there wasn't solver issues causing penetration problems with those. They're not crazy heavy, but they're a little bit heavier than the faster moving gears, which they need to be lightweight, or they at least need to have like a small inertia tensor so that they respond quickly to the forces that are being applied to them. Otherwise, the escapement doesn't work properly. Anyway, I think it's a cool project. Hope you guys enjoyed it. And here, let me pull the escapement back in. And we'll get it running. Oh, it's not quite in. There we go. And back to normal. Anyway, a pretty slick project. Hope you guys enjoyed it. Let me know if you have any questions, comments, concerns, and we'll see you in the next one. Thanks. Bye.